we've seen that this matrix leads to this equation, which with this assumption leads to this solution. We have repeated eigenvalues, so that this eigenvalue leads to this solution. This eigenvalue, following the same procedure, would lead to the same solution, which is certainly, or at least a multiple of the same solution, certainly not going to be linearly independent. So we need to find a linearly independent solution. Trial solutions of the form y2 equal e to the 5t, which is our original 5 is our original eigenvalue. So there's our e to the lambda t times v, where v is to be determined. Turns out not to work. Multiplying this by t and hopefully finding a solution for v, that doesn't work either. You can work out some details and see why that doesn't work. But this motivates us to try this solution. Now there are other deeper level motivations for doing that, but let's just go with what we've got here. Okay, so that if y2 is this, we found that y2 prime is this expression, and of course that should equal a y2, which should then equal 5 times the y2 vector. Setting this matrix product equal to this vector, and doing a little bit of manipulation with the matrix product, specifically factoring out the constant functions and using the linearity of the matrix, this matrix product becomes t e to the 5t, bad marker, t e to the 5t times a v1 plus e to the 5t times a v2, and that should equal this y2 prime expression, which is e to the 5t times 1 plus 5t times v1. Got that arrow in the wrong place. And I got the parentheses in the wrong place. I'll put another set of parentheses there. Plus 5e to the 5t v2. Now we have the e to the 5t common to every term, so we can simply write this dividing through by the e to the 5t, which is always non-zero, so that we can safely divide by it. We end up with the equation we see here. And now the multiples of t on both sides have to be equal, and the non-multiples of t have to be equal. T is variable, so that the TAV1 is going to have to equal the 5t v1 for all values of t. This gives us the solution TAV1 equals 5t v1, not the solution, but it gives us the condition on our solution set that this must be the case, and then our condition on v2 is simply that a v2 equal 1 times v1 plus 5 v2. Dividing the sides of this equation by t, we end up with a v1 equals 5 v1, and a v2 minus 5 v2 equals v1. The second equation is going to give us a v1 AV2, I'm sorry, minus 5v2 equals v1. Now, what we have here is simply the eigenvalue equation, the eigenvalue equation, AV1 equals lambda v1 for the eigenvalue we've already found for A. so that V1 could be, for example, our first solution. V2, well, let's just do a little something here. First of all, I'm going to write this as a minus 5I V1 equals 0. And we'll write this as a minus 5I V2 equals V1. Now, as I mentioned, we can easily find a solution. We've already got a solution that will work for V1. The question is, how do we solve this equation for V2? And that could lead to some problems because, of course, we know that the determinant of this matrix A minus 5I is non-zero. Is 0. That was the condition that led us to our eigenvalue 5. So that we can't invert this determinant, or we can't invert this matrix and multiply by V1 to get V2. It just isn't going to work. So our question becomes, how do we solve this if we can't invert this matrix? Turns out, in this case, that we'll be able to, fortunately. Again, V1 is just any solution to our original problem. Now we see that, remember that 1, negative 1 was the solution we originally found, the eigenvector for the equation a minus lambda I x equals 0 when lambda is equal to 5. We found that solution previously right here, obtaining this eigenvector. So we let V1 equal that eigenvector. And that's our solution to this first equation. The solution to the second equation, which is a minus 5I times V2 equals V1, becomes what? Well, a minus 5I, just as before, is the matrix negative 2, negative 2, let's see, it was 2, 2, right? Multiplied by x1, x2 should be equal now to V1, which we've chosen to be 1, negative 1. Remember, V1 could be any solution to this equation, but any solution is going to be a multiple of this solution, so this solution is as good as any. Okay? Now, we simply solve that for x1 and x2. What do we get? We get negative 2x1 minus 2x2 equals 1, or 2x1 plus 2x2 equals negative 1. Fortunately, and this will always turn out to be the case, these two equations are again multiples of each other, even though over here we don't have 0, 0 anymore. We still find that the two equations are multiples of one another, and it's not too hard to prove that that's always going to be the case, with certain fairly broad restrictions on our original matrix. Now, just as before, we don't get a specific solution for x1, x2. Our solution to this equation, if we solve for x2, is going to be x2 equals what? Negative 2x2 is going to be 1 plus 2x1, so that x2 is going to be 1 plus 2x1 over negative 2, or negative 1 plus 2x1 over 2, which is x1 minus 1/2. That's going to work for any x1 we might want to choose. So we might as well let x1 equal 1. And that gives us x2 equals 1/2, meaning that our v2 vector is 1/2. Now we have our v1 vector here, we have our v2 vector here, and why do we have a v1 and a v2 vector? Well, that goes back to our original assumption that we have a solution y2 equals t e to the 5t v1 plus e to the 5t v2. All we have to do is plug in our v1 and v2 vectors now, and we have a solution to our system. So, just rewriting what we wrote here, our assumed solution. Our solution is now equal to the assumed solution for the vectors v1 and v2 that we've found here, so that the solution is going to be t e to the 5t multiplied by the v1 vector, which is 1, -1, plus e to the 5t times the v2 vector, which is 1/2. And that's e to the 5t. I said it, I didn't write it. So finally, distributing and adding up, we get y2 is t e to the 5t plus e to the 5t and negative t e to the 5t plus 1/2 e to the 5t. Now our first solution was y1 equals e to the 5t times 1, -1. We now have a second solution, which we could write, if we wish, to factor out the e to the 5t as e to the 5t times t plus 1, excuse me, negative t plus 1/2. So that our solution set is our y1, which is e to the 5t times the vector 1, -1, and e to the 5t multiplied by the vector t plus 1, negative t plus 1/2. We can check that the Wronskian, which is the determinant of our psi vector, equals something that's not equal to 0. Now you can check that on your own. And I'm writing uphill again. The general solution to our original system, which you can also check, and it's possible that I've got an error somewhere in these calculations, although I've been fairly careful. Our general solution is y of t equals c1 e to the 5t times 1, -1 plus c2 e to the 5t times t plus 1, negative t plus 1/2.